Hello everyone. Today I'm going to do an overview of generative image models. This includes variational autoencoders, generative adversarial network, diffusion models, and flow-based models. There are many well-known applications from different parties you might already know. For example, Stable Diffusion, Midjourney, OpenAI's DALL-E, Google's Imagen, all belongs to it. As LLM and AI goes beyond pure text, multimodal, especially image generative models, will become more and more important. Let's dive into it. In this generative image models overview, we're going to go through all the model types from a very high level. We are going to build intuition, understand the basic mechanism, get familiar with the high-level architecture, and the applications. We are not going to deep dive into the architecture details, or the training and sampling details, or the mathematics behind it. Those topics is going to get covered right after this overview in the deep dives. Please stay tuned. Let's step back a little bit and start with the model categories overview. In machine learning models, you can generally classify it into discriminative models, predictive models, and clustering models, and generative models. And for generative models, there's usually autoregressive, VAE, GAN, diffusions, and flow-based models. The one that I mark as pink is what we want to cover today. Let's go through the other one really quick, just for completeness sake. Discriminative model is used in supervised learning with known labels. They are usually classifiers to identify relationship between features and labels. For example, a discriminative model can differentiate image that is fake or real, and it's used in GAN. So the category here is not exclusive. It's possible that some of the model is used in the other one. Predictive model is using historical data to predict future data. Clustering model, it's used in unsupervised learning to group dataset into clusters based on similarity. In generative model, it's to learn the underlying patterns and distribution of data from the observed dataset. This is to enable us to create new data samples that resemble the training data. So given observed samples X from distribution of interest, we want to learn to model the true data distribution. This is what we want to focus here. And within the generative models, we are not going to spend too much time on autoregressive model in this video. If you're interested, you can check my transformer video for details. This is more popular in text LLMs. It's used occasionally in other models like Diffusion and DALL-E. We are going to mention it several times, but we won't spend time on it specifically. Let's start with autoencoder. Autoencoder is composed of an encoder that learns to isolate the important latent variables from training data, and a decoder that uses those latent variables to reconstruct the input data. And for the latent space, you can also call it bottleneck. Latent variables are underlying variables of data that inform the way of the distribution, but are often not directly observable. A good example is Plato's allegory of the cave. So there's a group of people that are chained inside a cave their entire life and can only see 2D shadows projected on the wall in front of them. Those shadows are generated by unseen 3D objects passed before a fire. To such people, everything they observe is actually determined by a higher dimensional abstract concepts that they can never understand. In this case, the 3D is latent space and 2D is observation. However, in generative image models, usually the latent space is lower dimension. Autoencoder have many applications. Apparently, it can do image compression. It can extract latent embeddings from image. It can also do image restoration, magic eraser, denoise. Those are using similar mechanism. For example, in training process, if we add noise to the input image, this is the input image, we add noise to corrupt it, and then we feed the corrupted input into the autoencoder. We try to reconstruct the actual original image. We can measure reconstruction loss by comparing the output and the original image. So in this case, we can slowly train the autoencoder to reconstruct from corrupted image. And during inference time, we pass in a noisy image. It can learn to reconstruct it to an image with much better quality. So this is a denoise example, and the magic eraser example is similar mechanism. Let's move to variational autoencoders. The goal of autoencoder is to reconstruct the original image. However, for a generative model, what we want is given the observed examples X from distribution of interest, we want to learn to model the true data distribution Px. So in plain words, we want to generate new samples that resemble the original input, not to reconstruct the original input. That's why autoencoders, it's not good for generative tasks. And also autoencoder are fixed, deterministic mapping and discrete on the latent space. For example, this is a latent space of a number classifying task, and you can see each color represents a number. If we want to sample a random point from this 2D space and feed it to the decoder, it will generate a new image that is similar to one of the 0 to 9 digit image. If we pick a point in the latent space right here, it will probably generate a pretty good 1. If we pick the point here, it's going to generate a pretty good 0. However, if we pick number here, it's going to be very messy, and we probably don't have a way to determine what is the best number it can generate. So that's why plain autoencoder is not good for generative model. That's why we want to have variational autoencoders. Variational autoencoders are probabilistic model. VAEs encode latent variables of training data not as a fixed discrete value z, but as a continuous range of possibilities expressed as a probability distribution pz, represented with mean vector mu and a standard deviation sigma. This is the graph that explains the difference between autoencoder and VAE. Instead of mapping the original image to a discrete fixed point, we're mapping the original image to a probabilistic distribution. So in the autoencoder, if the random point is not explicitly mapped before, it kind of is meaningless, especially if there's no good way to determine its closest point. For example, in this case, we don't know which explicit mapped point to pick for this meaningless point. However, in VAEs, since everything is distribution and the space is continuous, no matter where we pick, we actually can sample and produce a new meaningful data based on the distribution. So this is the architecture of the VAE. It's pretty similar to autoencoders. We still have the encoder, we still have the decoder, we still have the bottleneck, but the bottleneck is represented by a mean and standard deviation. Let's move to conditional VAE. With VAE, we can sample a random point in the latent space and generate new images similar to training set. However, there's no control. Say we want to generate a specific number with the previous data set instead of a random one. How can we do that? That's why we have conditional VAE. Conditional VAE has an extra input to both the encoder and the decoder, usually in one hop vector. It's basically the label. So during training time, let's say we want to use one hop vector to represent the number 4. An array that is of length 10 represent 0 to 9. So the fifth element represent 4. In this case, the one hop vector, everything is 0 but the fifth element. So we pass the image and the label to encoder. We also pass the label to the decoder. In this case, both the encoder and decoder will learn the image that it's encoding and decoding is actually of number 4. And after the training is done, when we want to do actual inference, we also pass in an additional input, one hop vector. So even if we sample the same point in the latent space, if our y vector is different, it's going to generate different numbers. So if we pass in number 4 as one hop vector, it's going to generate this image. If we pass in 7 as one hop vector, it's going to generate this image, even with the same point in the latent space. So this is the overview of VAE. There are more details we're going to cover in later episodes. Let's move to the next topic, generative adversarial network, GAN. So this is an example of what GAN can do. It was amazing when it got released. It's still pretty amazing right now. So let's quickly go through how it's achieved. Generative adversarial network, it consists of two models, a generator and a discriminator. They're trained in an adversarial process, where the generator tries to create data that looks realistic, and the discriminator tries to distinguish between real and generated data. So during training, the generator takes random noise as input and generates data samples, whether it's images, text, or audio, that it hopes it will fool the discriminator. The discriminator takes both real data and the generated data from the generator as input and tries to determine whether the input is fake or real. So the goal is for the generator to reach a point where the discriminator can no longer reliably distinguish between real and generated data. That's the point where generator, you can use it to generate new real-like fake images. So post-training, we only use generator to generate images. So this is a really simple graph of how GAN is working. We have random noise we pass into generator and it's going to generate a fake sample. And we have real images that generate real samples. We pass into discriminator, and discriminator is going to determine whether it's real or fake. And since we have the label whether it's actually real or fake, we can calculate discriminator loss and the generator loss. And we can update discriminator and generator accordingly. So this is the first training phase. We want to train the discriminator. In this case, we want to have n real images and n fake images produced by generator. They are given to the discriminator to classify each image whether it's fake or real. And for the real image, we have the label equals to real. For the fake image, we have the label equals to fake. Labels are used to calculate the loss later. Discriminator's weights are updated based on its loss. So after discriminator tells us whether the image is fake or real, we compare it with the actual label, and then we compute the loss, and then we update the discriminator model. In the first phase, we do not update generator model weights. We only want to focus on discriminator training. And in training phase 2, we want to train the generator. And in this case, no actual image are used. We want to generate n fake images by the generator model and feed it to the trained discriminator asking for classification. And the trick is we want to label all the images as real, although it's fake images. So in this case, if discriminator classify it as fake, and this is a negative feedback for generator model. If the discriminator classify it as real, and this is a positive feedback, generator, you're doing a good job. So we update the generator weight with the loss calculated. We do not update discriminator weights. We then repeat phase 1 and phase 2 many times until the generator is good enough. So it sounds pretty simple, but there are actually many challenges in GAN. First, the data quality and quantity. GANs often require high quality and very large data sets to train effectively, and the training is actually pretty unstable. Generator and discriminator fails to reach a stable equal state, leading to oscillating or diverging behavior. And generator is especially hard to train. Usually discriminator can have almost zero loss, meaning even when a generator is already generating a realistic image, discriminator can still figure it out. So then in this case, the gradients used to train the generator can become very small or zero. This makes it very difficult for the generator to learn and improve, even if the discriminator is still improving. There are many ways to solve it. We can add noise to discriminator inputs on purpose, or we can even make the labels noisy, so we confuse the model intentionally. It's also possible to have mode collapse. The generator only produces a limited number of outputs instead of the variety that is desired. For example, in this case, the training data points have all numbers. The GAN generated data point only have 0 and 1s. This is to visualize it, so the actual distribution is a lot wider than the generated distribution. So there are many challenges with GAN, and they have different solutions to solve it. And we're going to go through those in the following episodes. For now, let's move to the architecture. So this is the GAN architecture. We have the generator, we have the discriminator. In generator, it's similar to the decoder and autoencoder. In discriminator, it's similar to the encoder and autoencoder. And it has the upsampling, and it has the downsampling, which is really convolutional. Similar to VAE, we want to have conditional GAN to somewhat control the generated images. And the mechanism is also very similar. So these two graphs are the training process of conditional GAN. The first one is training discriminator model. The second one is training generator model, similar to the previous GAN graph that we have already gone through. And in this case, the only difference is one hop vector that represent the labels. If we want to use the example of the sunflower drawings, we can transform the text sunflower drawing into a one hop vector embedding, and we pass it into discriminator and generator. So in this case, the discriminator training process is going to have context of the one hop vector. And when we train the generator, we do the same, pass in the labels to generator and discriminator. So the generator also have context of the one hop vectors. This is the discriminator input. We have the actual images, but then we have the matrices of one-hot vectors. There are more type of GANs. For example, cycle GAN, it can transform one image to the other, preserving some of the styles. We have an even more magical controllable GAN, which can basically modify any details on your face. Stay tuned in the following episodes. Now let's move to diffusion models. Diffusion model is currently the most popular implementation. For example, Midjourney, Stable Diffusion, Google's Image Gen, OpenAI's DALL-E, starting from DALL-E 2, those are all diffusion models. The intuition is for images in the training dataset, diffusion models gradually add noise to the original image, step by step, until it's fully destroyed to pure noise, which is really normal distribution. And then we learn to reverse that diffusion process and reconstruct the original data distribution. First, in the forward distribution process, we slowly corrupt the image until it's noise. In the reverse diffusion process, transform noise into the original image. So a trained diffusion model can generate a new image that resembles the training data by simply denoising a random initial sample of pure noise. This is similar to a denoising autoencoder that we have covered previously. So the method here is to train an encoder-decoder model, take a noisy image as input, and predict the noise so that the original image can be reconstructed by subtracting the predicted noise from the input image. This is a bit indirect, right? So why are we not predicting the original image? We're not predicting the original image since our goal is not to reconstruct image like autoencoder. Our goal is to get the underlying actual distribution to generate new image. So more details is in the following episodes. So for now, knowing this is enough. The loss can be computed based on the difference between the actual noise and the predicted noise. To training diffusion models, there are several steps. The first one is forward diffusion process. Image is transformed into pure noise. It's basically standard normal distribution in T steps. You can view this one as a fixed Markov chain with T steps, where the image at timestamp T maps to its subsequent state at timestamp T plus 1. So each step depends only on the previous one. This is basically the definition of Markov chain. Standard deviation noise is added at each step in the Markov chain, and it's not constant or arbitrary. Instead, the noise is derived from the structure of the original image, and the rate at which it's added steadily increases with each consecutive step. This is all determined by its scheduling. More details again in the following episodes. I apologize if this appears to be not disclosing everything in one episode, but the truth is it's almost impossible to cover everything in 30 minutes or even 1 hour. The next process is reverse diffusion process. This is where the actual machine learning happens. So we want to directly transform random noise into a new image if it's possible. But it's extremely difficult and complex. But transforming a noisy image into a slightly less noisy image is relatively easy. So diffusion models therefore formulate the reverse diffusion process as an incremental, iterative transformation of Gaussian noise to actual images. So you might think a simple reverse of the forward diffusion process will work. In this case, we want to reverse this function to the Q function. But in practice, computing Q given t minus 1, we want xt. This is almost impossible. So instead, the model predicts the entire noise present in xt and then removes a fraction of that noise to get to xt minus 1. More details in later episodes. So this is the architecture of diffusion model. I pulled it from online. If it's too complex, we can take a look at the next one. This is the TLDR of diffusion models architecture. It has the downsampling process, it has the bottleneck, it has the upsampling process. And for your knowledge, this is a UNet-like architecture. So UNet is a very, very old architecture. The input and output size are identical. And within the architecture, there's skip connection between downsample blocks and upsample blocks. And if you're not familiar with the skip connection, take a look at my transformer videos. There's also self-attention blocks, similar to what we have in the transformer. So this is to predict the noise of image. And also timestamp is passed in as sinusoidal embeddings, again, similar to what we did in transformer. If you want to know more details right now, you can actually check my previous video. So similar with the previous one, let's say we want to have some control over what we want to generate on diffusion models. This is where the guided diffusion models come in. And the mechanism again is very similar. We basically want to pass in the label as one hot vector or embedding in the training and sampling process. In this case, let's say we're trying to generate new images for number 4. So we want to pass in number 4 as a one hot vector into the UNet, and then the UNet is going to predict the noise, and then we subtract this noise from this noisy image, then we should ideally get the original image. By comparing the predicted noise with the actual noise, we can calculate the loss and update the weights for UNet. And after this UNet is trained, we can actually use a completely different text, let's say number 4. After it's transformed to embedding and passed the trained UNet, the trained UNet should be smart enough to predict the noise, and after subtracting the noise, it can generate a new style of number 4. So this one is of the same style, but actually it can be different. Next topic I want to cover is latent diffusion. You might know it as stable diffusion. So the motivation for this is training and sampling of diffusion model can be very, very expensive, computation and memory wise, since it requires multiple denoising passes. So can we introduce a lower dimension latent space and perform diffusion there? Stable diffusion was invented from this motivation. It performs the diffusion process in the latent space. For TLDR, we have a trained encoder to encode a full-size image to a lower dimension representation, aka the latent space. And then we have the forward diffusion process and the reverse diffusion process within the latent space instead of the original pixel space. So then trained decoder can decode the image from its latent representation back to the pixel space. This is the architecture of the stable diffusion. As you can see, there's QKV, cross attention from transformer appears again. The key and value are from text prompts, and query is from the latent representation of image. In this case, we can use the text prompt to control what we want to do with the image. For more details in the following episode again. The next one I want to briefly cover is flow-based model. So the intuition is our goal is to generate new images out of pure noise. So what if we learn a function fx that maps images complex data distribution to a normal distribution, and then we use a f inverse function to convert a random sample from the normal distribution space to generate a realistic image. So if we have this magical function f, then generating new image should be very simple, right? So this is an example of mapping the complex input data distribution to a normal distribution. So this is an example of the magical function fx. And this is the training process and inference process of the flow-based model. So during training for images within the training datasets, we wanted to go through a magical function fx or stacked flows and transform it to the latent space z. And the inference process is we sample a point in the latent space and then inverse the function fx or the stacked inverse functions, and then we should generate a new image. So in this case, the latent space is the same dimension as input, and there should almost have no data loss. With this magical function fx or stacked function fx's, we can generate new real-like fake images by sampling random point in the latent space. So more details about this magical function in the following episodes. Let's do a quick summary. For VAE, we pass in input data into the encoder, and then we transform it into the latent space. In the latent space, we can sample random points through the decoder and generate new images. During training, we want to maximize the elbow as target function. I'm going to cover the mathematics behind it in the deep dive in VAE. So for GAN, we have the adversarial training. We train discriminator and generator, and discriminator is going to learn to classify real and fake. Generator is going to generate images better and better until a point discriminator cannot determine whether it's real or fake. Then we can sample a random point in the latent space and ask generator to generate new images. For diffusion, we gradually add normal distribution noise and then reverse the process. For flow-based, we have a magical function fx that can transform real images to a normal distribution. And then if we inverse that magical function, we can transform normal distribution to actual new images. So those are the summary of generative image models. Hope this is helpful. What's next is we're going to have autoencoders and VAE deep dive. Also, GAN and its variances deep dive, and diffusion model deep dive, and flow model deep dive. And we're going to have a separate one just for DALL-E and DALL-E 2, because this is a very interesting case. For the first one, it's not diffusion, and for the second one, it's diffusion. So stay tuned. If you like my video, please subscribe, comment, or like. See you in the following episodes. Bye.